Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to calculate ionization energies of a lithium atom. So let's get into this. So in this problem, we're told the energy needed for the following process is 1.96 times 10 to the 4 kilojoules per mole. And what is that process? That process is where you take lithium atom in the gaseous phase and you remove 3 electrons, and you end up with the lithium atom with a 3 plus, and you have 3 electrons removed. If the first ionization energy of lithium is 520 kilojoules per mole, calculate the second ionization energy or second ionization of lithium. That is the energy required for the process that we see here. So this is the second ionization of lithium. So you remove the first electron from lithium, you end up with a lithium plus charge on the atom. And then when you remove the second electron, you're going to remove it from Li plus to get Li2 plus, and then you got the electron. So that's the setup. And so we're asked, what is the second ionization? Okay, so we got to kind of put this together. So let's kind of recap what we're given. So we're given the process of removing 3 electrons, and they give us the total energy to remove those 3 electrons. So you're removing the first electron, that requires a certain amount of energy. You remove the second electron, that requires a certain amount of energy. And then you remove the third electron, and that requires a certain amount of energy. And the total of those 3 energies is going to be 1.96 times 10 to the 4 kilojoules per mole. Now, let's write that out. What that means is each time you remove an electron from an atom in the gaseous state, that's the ionization energy. So the first electron is the first ionization energy. So we'll write ionization 1. So IE1 is the first ionization energy. That was the energy needed to remove the first electron. And then the second electron, if we add to that, that's going to be the second ionization energy, so IE2. And then when we remove the third electron, we're going to add the IE3, the third ionization energy. Let me write that better. And so the 3 ionization energies added together is going to equal this one. So that's equal to 1.96 times 10 to the 4th kilojoules per mole. Okay. So what else do they tell us? They say that the process, so for the first ionization of lithium is 520 kilojoules per mole. That's the ionization energy 1. So IE1 is 520 kilojoules per mole. So that's this here. So they're giving us that. So we're going to write that down. IE1 is equal to 520 kilojoules per mole. So we can plug this in for IE1 in our equation here. So this is going to become 520 kilojoules per mole plus IE2 plus IE3 is equal to 1.96 times 10 to the 4 kilojoules per mole. Now I can subtract this ionization energy from both sides, and I'll get IE2 plus IE3, and I'll get the total for those two. So I'll subtract 520 kilojoules per mole from each side minus 520 kilojoules per mole. So then this cancels out, and I'm left with IE2 plus IE3 equals, and then whatever that is, and when I subtract that, I get 1.908. So 1.908 times 10 to the fourth. Again, that's kilojoules per mole. Okay. So now that I have this, so I know that IE2, this is the second ionization energy, plus the third ionization energy is going to be equal to this. So now I have these two unknowns. Well, what do I do? Well, here's where you have to kind of think about this part here. So we're given this process here. So this is the second ionization energy. Well, what does the third ionization energy mean? Well, if we draw the Bohr model of the lithium atom, the lithium atom only has 3 electrons. So the first electron that's removed is the valence electron, the outermost shell in the second shell. So removing that one would be your IE1. Removing one of these two would be your, your IE2. So after you remove the second electron, you only have 1 electron left. Removing that electron would be the ionization, the third ionization energy. So the third ionization energy is the removal of the last electron from the atom, 1 electron. So after you remove these 2 electrons, you have a 1 electron system. You have a hydrogen-like atom. And so in that case, you can use the Rydberg equation for figuring out the ionization energy. What is that equation? Well, it's not the Rydberg equation, but it's a derivative of. That is the change in the energy of the atom is equal to negative z squared times 2.18 times 10 to the negative 18 joules multiplied by 1 over NF squared minus 1 over NI squared. And that is the equation. This equation works fairly accurately for any 1 electron system, any atom that is like hydrogen having only 1 electron. So the Z here represents the atomic number. So remember, if you remember, the atomic number is represented by the letter Z. And so this is referring to the atomic number of your atom. Typically, but more precisely, more exactly, this is referring to the effective nuclear charge, which is not always going to be equal to the total number of protons in your atom. However, in this case, when you remove all of the electrons, you only have 1 electron left over, so there's no shielding going on, there's no penetration, you don't have to worry about figuring out what the effective nuclear charge is, because there's no shielding going on, so this electron feels the full force of the nucleus. So whatever number of protons in the nucleus, that's going to be your Z. Your NF, this is the energy level for the final energy level that your electron is in. And this is the energy level that your electron starts in. So this is used to calculate the transition of your electron from one energy level to the other. So where did it begin? What energy level did your electron begin? What energy level did it end in? And so we can use this to find the third ionization energy. So the third ionization energy is going to be equal to the change in the energy of the atom, which is going to be equal to this. So let's go ahead and plug the information in. Lithium has 3 protons, so it's going to be negative 3 squared times 2.18 times 10 to the negative 18 joules. Okay, so what is the final energy level that the electron is in if you're removing the electron from the atom? Well, remember, the closer you are to the nucleus, right? The closer you are to the nucleus, the lower your n number is. So here we're going to have n equals 1. So this energy level is n equals 1. This energy level is n equals 2, and so on. So the farther away you get from the nucleus, the number of the energy level is going to go up. Well, if you're removing the electron completely from the atom, well, this n is going to go up infinitely, right? So the last energy level is infinite, right? So we're going to remove this infinitely away from the nucleus. So this is going to be 1 over infinite squared. And infinite squared is infinite. And then so we're going to subtract that from our starting energy level. Well, the starting energy level for the last electron is going to be in the n equals 1 energy level, right? Because we removed the first electron here, this electron was from the outermost energy level, so we remove 1 there. And then we go down to n equals 1 and remove the second electron from there. And then the third electron is removed from the n equals 1 level as well. So this is going to be 1 over 1 squared. And then if we kind of simplify this a little bit, this is going to be 1 negative 9 times 2.18 times 10 to the negative 18 joules multiplied by, well, what is 1 divided by an infinite number, an infinitely large number? That is going to be 0, because remember, as the denominator gets larger, then this whole thing is approaching closer to 0. It's getting smaller and smaller and smaller. So if you go an infinite number, then this is practically 0. So this is going to be 0 minus 1 divided by 1 squared is going to be 1. So 0 minus 1 is negative 1. So the negative here is going to cancel out with a negative there. So then it's just going to be 9 times this number. And so when I multiply all of this together, I get 1.962. 1.962 times 10 to the negative 17 joules. Okay, so I've now calculated my delta E of the atom. This is the change in energy of the atom, and that is equal to the third ionization energy. Now, before we go on, we need to note that ionization energy is normally given in kilojoules per mole. Notice this is kilojoules per mole. This is kilojoules per mole. This is joules per one atom. So joules per atom of lithium. So I need to convert this to kilojoules per mole. So let's go ahead and do that. I'm going to erase this because I don't need it anymore. Actually, I do need that one. Let's see. So before I calculated EI, the second ionization energy plus the third ionization energy was equal to, what was that number again? 1.908. So 1.908 times 10 to the 4 kilojoules per mole. So now I'm going to convert this to kilojoules per mole. So I have 1.962 times 10 to the negative 17 joules over 1 atom of lithium. So I'm going to convert joules to kilojoules. I know 1 kilojoule is equal to 1,000 joules. So I'm going to put 1,000 joules on the bottom. That's going to cancel out joules and joules. And 1 kilojoule on top. So joules cancel out. Now I have kilojoules on top, so I'm done with the top. So now I want to convert the bottom from atoms to moles. So I'm going to use Avogadro's number. I know 1 mole of particles is equal to 6.022 times 10 to the 23rd. So I'm going to put, since I have atoms on the bottom, I'm going to put atoms on top. So that's 6.022 times 10 to the 23rd atoms. And on the bottom is going to be 1 mole. So then atoms cancel out. Now I have moles. So now all I need to do is multiply and divide. And when I do this, I get 1.1815. 1.1815 times 10 to the 4th, I believe. Yes, 4th. And that's kilojoules per mole. Okay, so, and remember, this is equal to IE3, my third ionization energy. Look here, I have this here. My second ionization energy plus the third ionization energy equals this. So now I have the third ionization energy in terms of kilojoules per mole. So now all I have to do is plug in the third ionization energy here. So that means IE2, the second ionization energy, plus the third, which is this. So I'm going to put in 1.1815 times 10 to the 4th kilojoules per mole. That's going to be equal to this here, 1.908 times 10 to the 4th kilojoules per mole. So now all I need to do is subtract 1.1815 times 10 to the 4th kilojoules per mole from each side. Subtract 1.1815 times 10 to the 4th kilojoules per mole. So of course this cancels out, and so I'm going to end up with IE2 is equal to the subtraction of these two, and when I subtract those, I get 7.265 times 10 to the third kilojoules per mole. And that, ladies and gentlemen, is how you find the second ionization energy in this problem. I hope this was helpful. If you enjoyed this video, if this helped you in any way, then please like the video, share the video, hit the like button somewhere over there. Also, do me a favor, please subscribe to my channel. It helps me out. Hit that notification bell. When you do, make sure you click all so you'll be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, or if you have a topic you want me to cover, just let me know. I'll do it for you. Thanks for joining me and have a great day.